I'd like to say a few words about the consequences of Lagrange's theorem because it's a very powerful theorem and it allows us to know a lot more about the orders of subgroups and elements of Lagrange of a group. So we start if G is a group and K is a subgroup. Lagrange's theorem tells us that the order of G is equal to the index of K in G times the index of K. And the consequences of Lagrange's theorem are really what we care about, more than this statement. And I'll separate these into the situation where G is finite versus where G is infinite. If G is finite, meaning there's finitely many elements in G, our consequences here, our main consequence is that the order of any subgroup divides the order of G. So, for example, if G had order 30, I would know that the only possible subgroups could have order 1, 2, 3, 5, 6, 10, and 15. This tells me more, this allows me to quickly eliminate certain subsets as being subgroups just by looking at their orders. So this is a really nice fact. A second fact that we'll prove in part 5 on the part 5 of D on the adventure sheet is that for any element of the group, its order of G divides the order of the group. And the hint that I'll give you here is to look at subgroups that G must be in. Okay, but then if G is infinite, we have different consequences. So if G has infinitely many elements, Lagrange's theorem is still true, but now we have infinity on this side of the equation. So one of these two factors, at least one of these two factors must be infinity. So what Lagrange's theorem tells us there is that either my subgroup K has infinitely many elements, or K has infinitely many cosets, meaning the index of K in G is infinite. K has infinitely many cosets. And so these are really nice consequences that help us better understand the possible subgroups and orders of elements in a group that we already know the order of.